Also, I will. No, open. Connect.
Luis,
No, it's not. There is no Windows. Don't worry. No. And it's okay. All of you connect to this in Italy. It's okay. I will put it here. Is K Hoot. Connect on this. It's okay. It's okay for all. It's okay. Doesn't work. You note this code when they will ask you this code. 3933753. Well, when they will ask you PIN, normally when I will see here who is, and put your your name or as you like. It's not nickname. There is 2 players. Already 2 person. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
e eu não trouxe o celular, Paulo?
6. I hope that because but I don't understand how to put it full. It will be questions about the Lie differential equation and answer, and you have to. But the problem, I am not able to. There is problem with the. I cannot. It changed the code. Sorry. Yes. But no, it's okay. They found, yes. But the problem, I cannot. I think you will, because I have problem with the computer. I cannot see all the page. I don't know. You know how to help, because the page it's like. I cannot see. I cannot see all.
Resolution.
Okay. Resolution is.
Monitor.
À l'échelle, maybe. Yes. Ah, it's okay. Now it's okay. Confirmer. And this close. Okay. How to? Ah, okay. Yes. Thank you. Oh, we start. We will start. Are you up, Claudia? You have question and you have 4 answer, and you can answer more than one. A delay differential equation with discrete delay can be solved as an ordinary differential equation. Yes, if the initial condition is continuous. No, never. Only if the initial condition is constant. No, only for small delay. A delay differential equation can be, with discrete delay, can be solved as ordinary. This, or this. You have time. Ah, there is a 6. Good. 2, 1, 0. Are you?
Try a zoom.
I don't know how to. Ah, yes, yes. It's good. More? Okay. Second, are you ready? Next. Ah, this is the score. Oh. I will not show you now. It's only this. Next question 2. Consider this delay differential equation and suppose that the delay is p over 2. All the solutions blow up. There is periodic solutions. All the non-trivial solutions oscillate. All the solutions will tend to 0. You have time. It's 39. I put 1 minute for each. Oh, the correct one is this one and this one. There is 2 correct. All the non-trivial solutions oscillate. And also because there is periodic, also this is tricky. Oh, Matus. Who is Matus? Okay, are you ready for the next? This is for R less than P over 2. There is a problem with the connection. There is problem with connection. Huh? That's because you have You don't have the connection. All people, all the connection. No, I think there is my computer. This it's appear. Next, yes, it doesn't work. This okay, but yes. Okay. Question 4. You have this the same delay differential equation, and suppose that R is bigger than 1 over E. All the solutions blow up, explode. All the non-trivial solutions oscillate. Only some solutions oscillate. All the solutions will tend to 0. It's okay. The correct one is only this one. Okay. This is the correct one. Question 5. The equation, this ordinary linear, can be transformed to this one. Yes, always, only if the delay is equal to 1. No, it depends on the parameters. Only in the case A equals to 0. Can this equation be transformed to simple one? No, because it's yes, because it's yes, I show everything. Yes. The correct one is this one. Oh, there is more. No, it matters. No, we cannot. We can all the time. The answer is number 3. Always. We can make change of variable. This is related to characteristic equation of this. Which one is the correct characteristic equation? This one, this one, this one, or this one? Yes. You like what? This game? Yes, it's make we do it too much in and you can write mathematics with. This is interesting. Oh yes. There is 6 that but there is 4 thinking that it's polynomial, and 3 that it's only R and beta. Oh, someone. Now about this. To have local existence and uniqueness, we need F continuous, F and F prime continuous and F prime bounded, F and F prime continuous, or F linear. To have existence, local existence and uniqueness. local existence and uniqueness. Because you didn't. Oh, the correct one is this one. F and F prime continues. It's enough to have local existence and uniqueness. Not F prime bounded, it's not necessary to have local existence and uniqueness. And this, to have now global existence and uniqueness. Global existence and uniqueness of the solution. F continues, F prime continues and F prime bounded, continues on F or F linear. Oh, this is good. Almost all, yes, this is, you need F prime bounded to have a global existence on all the interval. Now we have this with the initial condition positive. And to have positivity, we need this condition, x y equals 0, f equals 0, or this is positive and this equal to 0, or this negative, or this equal to 0 and this is positive. To have positivity of the solution, if the initial condition is already positive. Which one we need to have positivity? This is bigger and this is equal. The red equal. Oh, good. This one, to need positivity, we put xi equals to 0 and we check that the non-linear part is positive, and to give you positivity. The principle of linear stability for the Lie differential equation means we can linearize every delay differential equation. Local asymptotic stability of linear equation implies local asymptotic stability of nonlinear one, or the stability works only for linear. This principle doesn't, I don't remember, differential equation. Maybe doesn't work, maybe. Yes. I forget something. We can linearize, or linear stability implies nonlinear stability, or the stability works only for linear. What that means, principle of linear stability. Yes, this the yellow one. Local stability of linear equation implies local asymptotic stability of the nonlinear one. Which one is correct? Which equation is correct? Mean modeling point of view. Here, AB minus A, B exponential, or minus A exponential, or exponential moves in each place. Which one is mathematical modeling point of view? Sorry? No, only one. Yes, it can be. First one can be also correct. But yes, but I mean, I don't want it, because we check. Yes, because here, as we jump the compartment, there is mortality in this compartment, and gives this coefficient, which is the survival rate of the compartment in the delay, because the delay make to jump. Okay, I think the next one. This is no, I hate. I don't know. Yes, for sure. This is the last. All of them are correct. Yes. Who is Matt? It's you. Yes. And you can view the report and. This is the statistics of each. Now we can analyze and come back to question that doesn't work. It's like a delay differential equation with discrete delay can be solved. Yes, can be always solved. This is the correct equation, and because we can do it by steps, first interval and second, etc. We can always solve it. If we have this, and for the delay equals p over 2, what was the question? I don't remember. It's if there is a solution, there is a periodic solution. When you take R, the delay equals p over 2. And this periodic solutions attract all the others and oscillate around. When you have this and same threshold, this threshold give periodic oscillations and instability. When your R is less than this, all the solutions go to 0. 0 is locally asymptotically stable. Okay, this gives stability of the steady state. 0 as steady state. This one, this threshold, when you go more than 1 over E, you have oscillations. Can be periodic or not. You have oscillations. Periodic is after P over 2. Here, all the solutions oscillate. Okay, this when you are more than this threshold. If the delay is less than this threshold, there are many solutions don't oscillate, but for the delay bigger than this, all the solutions oscillate. This equation can be transformed to yes, all the time. All the time we can transform this and write it like with delay equals to 1 and put alpha here. I did it. You make change of parameters and the characteristic equation for this is yes, we look for exponential. It's lambda plus beta exponential minus lambda r equals to 0. This is the characteristic equation of this. And for a nonlinear case, to have existence and uniqueness, we need f to be differentiable and the derivative is continuous, and it's enough. If f is continuous, you have only existence. You don't have uniqueness. If f is differentiable and the derivative is continuous, you have local existence and uniqueness. And if f is the derivative is also bounded, you have global existence. The interval of existence is all from minus r to plus infinity. For this discrete delay, if we have positive initial condition, to have positivity, you take the component, each component, you put 0 for xi, for this, and you check that the nonlinear part is non-negative, and you have positivity. The principle of linear Z stability is to tell you that stability of linear system implies the local asymptotic stability of the steady state of the nonlinear system. And which one is correct? It was because as we come, in general, you cannot take, if the production rate is B, as you go to a compartment and come back, there is mortality, and these compartments takes time equal tau. Then you have to add the survival rate, and the last one is 100%. It's okay, no comments. Okay. Now we have statistics to see. Yes. Okay. We can check. Sorry? His name? Because he put math pics?
Yeah.
Yes, you can.
No, but he was not among the top 10 when you list. There is a bug in your code.
There is a, I don't know. But you didn't play. Next time you will play. Okay, I don't remember when I stopped. I think it's yes, we were talking about Mackay-Glass equation, which the production and the regulation of blood cells in the bone marrow. And the mature cells, which are in the bloodstream, are regulated by the compartment of immature, and also the compartment of immature cells are regulated by mature cells. I already, yes, this is the equation that McKay and Glass introduced for to study the regulation of blood cells in the bone marrow. This is the degradation of cells, and this is the production. There is delay because the production happens in the bone marrow, and tau, I think it's about 1 day, 24 hours, that he make estimation. And yes, beta is a function of x, and it's given by this. Beta, it's what we call Hill function. It's a decreasing function, and maybe there is a, yes, this is beta, the shape of beta. Beta x times beta of x has this shape. This is the maximum. If the number of cells is very low, beta is big, and if it's big, beta is small. And there is here in the middle this parameter that is half of the maximum. And the parameter n that I talk here make, what is this parameter? What we call sensitivity. If you increase this parameter, you increase here the inflection point. You make like this movement, and it allowed this function to be to decrease more fast or slowly. Okay, we can here make a change in the model and normalize the equation by multiplying by theta, and you obtain this. You can put theta equals to 1, because if you divide this equation by theta n, you will have here 1, and here x over theta, and you can put also change here to by multiplying by theta or dividing by theta, and you will have equation doesn't depend on theta. And this is maybe I will show you next time, but I will talk about here because it's important. This function here, we can see that there is a part without delay, and there is a part with delay. Okay, and this part, which is non-linear, has this shape. Okay, and this is here linear. If we look for a steady state, then here we have a line. Okay, and the intersection between this function and this function give you the steady state. Okay, for 0, this function also comes from 0, and you have this. And we can, for example, the steady state is 0 and this one. If you are here, there is only this steady state and this one. And the theory that I will show you next time, if the steady state is here, you will have oscillations. If the steady state is here, you will not have oscillations. The part where the function that contains the delay is increasing create what we call a monotone dynamical system, and you will never have oscillations when a system is the dynamical system generated by delay differential equation is monotone. Monotone means monotone in terms of this. I will show you exactly what that means next time. And in general, we can see very quickly if there is oscillations or not. I am not saying that here automatically oscillations. What I want to say, if you increase delay, you will met oscillations. For the steady state here, you can increase delay as you like. You will never have oscillations. In this part, you will have local stability, And by increasing delay, you will have creation of oscillations. In this part, the steady state will be globally asymptotically stable without any oscillation. And this why we can do it here and not here, because here we have a principle of comparison that I will show you. We can compare this with a linear function that is more easy to study. I already, but here sometimes I give you the condition to have positivity, which works all the time, but almost all the time we are lazy to check for this and we do it by hands. Okay, it's like a proof. To do it by hands, it's by contradiction. We assume to prove positivity, we suppose that we don't have positivity. That means there exists capital T such that X is positive before and it becomes 0, because to be negative has first to be equals to 0. And this is a contradiction, can never happen here. Why? Take T here equals to capital T. This is 0 because you suppose that this is 0. And this is positive. And you have this expression. Okay? That means if this is positive, it is 0, the derivative of this expression is exactly this positive term. And this is not possible because you have positive solution and go to 0 with positive derivative. It's not possible. If it's go to 0, derivative has to be negative. This is why the condition that I give you before works, is exactly this, the proof of this assumption. Then we deduce as there is a contradiction. That means we will never have this. That means x of t is greater than 0. And all the time when you have a positive term here, the term that where is the delay, and the other one can be equals to 0. When you have this term, you have positivity all the time. Because the delay appears in the production term, in this term. We look for steady states, equilibrium. They are constant solution. That means if you put here x constant, you put here also x constant, because if x doesn't depend on the time, it will not depend on t minus tau. Then you have this expression, and you put gamma x on the left, then you have gamma x bar equals beta 0 this. And you can see immediately that 0 is always the solution. And there is another solution if you simplify by x bar. This means that as we are talking here about cell production, this steady state means that the cells will disappear, and this is give you a positive steady state. This one always exists. Okay, but the positive steady state will exist if and only if, and we can find the condition. This has to be bigger than 1. Then the condition is beta 0 greater than gamma. If gamma is bigger than beta 0, this steady state will be only the steady state. And if beta 0 is greater than gamma, then we will have two steady states, 0 and the positive one. And this is looks like normal, because this is the mortality and this is the production, the maximum production. If the production is bigger than mortality, you have two steady states. And if the mortality is what we call apoptosis, if the mortality is bigger than the production, you will have only 0 as a steady state. And in the case where B0 is greater than gamma, we can compute the positive steady state, which is given by this expression. Okay, and we can see that this steady state, in fact, is connected to 0, because the threshold is beta 0 greater than gamma. If you take beta 0 equals to gamma, it will be 0. That means if you compute, you will have 0 and the other one positive, but he will start, if you move, for example, beta 0, he will start from 0. Then, yes, this is only to summarize this. The Mackay-Glass equation has a trivial steady state and a unique positive steady state if and only if beta 0 greater than gamma. We can, I will come back to linearization. We can make linearization around each steady state of this equation. And you can see here, the equation has this form. Okay, we can separate the term without delay and the term with delay. And if we make this one, it's x1, this one is x2, the nonlinear, the function f has this form, minus gamma x1 plus b0 x2 over 1 plus x2 n. And the steady state is to put this constant and this constant. The steady state is given by this expression. Okay, both are are constant, the same constant. Okay, it's only to tell you that this function has this form. We can separate the term without delay and term with delay. And why I am talking about this? Because the linearization of this kind of function, it's very easy. It's given by this expression. Has always this form where the parameter a, which is here, is given by the first derivative of f on the steady state, the first derivative in terms of this component, and the second parameter, which contains delay, it's given by the derivative of the function f in terms of the second component on the delay. The derivative of this is minus gamma, okay, and the derivative of this one is given by this expression. If you calculate derivative here, you will have exactly this. 1 minus n minus 1 x n, etc. And we can see, for example, if you take 0, the steady state here, you will have beta 0, because this is 0, 1, and here 1. And we can now, this parameter is always negative, but this one can be positive or negative. It depends on if n is big or not. And it depends also on the steady state that we choose. Okay, let's start with the trivial steady state. The parameter a is minus gamma, he is negative, and the other parameter is b0, and it's positive. Then we have this this characteristic equation. And remember, I don't know if I put, I didn't make, how to say, if it's, I don't know if I put it after or not, stability of the steady state. No. Yes, I will do it. Now I am talking about only linearization. Okay. This is the linearization of the equation around 0. For the positive steady state, we need this assumption, and we have the same. We calculate a is always minus gamma, and the other steady state is given. Why I put negative? I have to check. Maybe, no, this is not true. It can be positive or negative. But if we put the steady state, this part, then we have the parameter b is given by this expression. This is not correct, because it can be positive or negative. Yes, we can see here. If n is bigger than this, then b is negative. If n is between 0 and this threshold, b is positive. Then we can now make characteristic equation. Remember this, and the characteristic is given by this expression. Here you have lambda, comes from the derivative, and you put this, the other part, minus a minus b exponential of minus r lambda equals to 0. And we look for complex root. Maybe this we can, why this, if beta 0, what that means, beta 0 greater than gamma, that means we have 0 and positive steady state. If the mortality is bigger than the prediction, we have only 0 as steady state. And it is locally asymptotic. Yes, I know why I put this, because I come back to a big result that we remember. Let me check. For this, A equals minus gamma, and this beta 0. Okay, let me come back to, yes, I think. Yes, the result is here. Remember that A is minus gamma, and B is beta 0. Okay? Then if we add A plus B, it's minus gamma beta 0. As if gamma is bigger than, if beta 0 is bigger than gamma, we will have a positive term. Then we are here. And then 0 is unstable. Okay? If now gamma is bigger than beta 0, more mortality than prediction. And this one, it's satisfied because you have minus gamma minus B0 is negative, then the trivial steady state is asymptotically stable. And this never happens because A plus B negative and A minus B positive cannot be satisfied by these two parameters. That means we will never have periodic solutions. We will never have threshold. That means the stability here doesn't depend on the delay. Okay? This never happened, and the stability never depends on the delay. This, in fact, exactly what I told you before, because this part, B is, beta 0 is always positive. That means if you plot this part with delay, you have this. Okay, it's positive. And the other one, because we have only 0, it's the intersection. And as this always positive, it's increasing. Then we have generates a monotone dynamical system. Then we have global stability of the only steady state that exists. Here we can prove that in that case where 0 is locally asymptotically stable, in fact is globally stable. I will prove it by Lyapunov function. For this, we can construct a Lyapunov function or use the general theory of monotone dynamical system. Always this has in mind. If you have something increasing for the delay, the part that contains delay, if there is steady state, this steady state is globally asymptotically stable. For the positive steady state, which is given by this expression, beta 0 greater than gamma, if we compute this, we have this, and this is negative, okay? A plus B, because beta 0 is greater than gamma. And A minus B, it's given by this. This we cannot know. It depends on N. Because you have beta 0 is greater than gamma. Let me, maybe it's always, I will see. Yes, because it depends on, there is minus. Yes, this is why I have here. Then use the same result that I show you. If beta 0 is less than gamma, then the positive steady state is unstable. No, this is not true. Oh, there is a mistake here. Because it doesn't exist here, sorry. Beta 0 less than gamma, this steady state doesn't exist. Then forget this. It's only because we have always gamma greater than, beta 0 greater than gamma. And A plus B is positive. We have to check only this condition. Only the condition, I come back. This we can forget because it's always satisfied. This always positive, A plus B. we have to look only for A minus B. And we have two conditions to have one. It's to satisfy this expression. I will come back to, this is our main result. Yes, it's related to A, the sum of parameter A plus B and A minus B. And I told you this one is always satisfied. Then we don't have this condition. And this one is satisfied under some conditions. And you have 0 is the steady state X bar is locally asymptotically stable, and it's independent on the delay. We have to check only the last one. Yes, and the last one, this one, it's independent on the delay because we have A minus B negative. But this one depends on the delay. If gamma is greater than this, then there exists a threshold of the delay such that the positive steady state is locally asymptotically stable if we are less, if R is less than the delay, and it becomes unstable when we go when R is bigger than the delay. And this is the last case. And we can prove also this, we can have explicit expression of this threshold given by this expression. Okay, this is very interesting because I will show you after that we can also, when we will reach this, we will have periodic solutions. Not only for the linear equation, but also for the nonlinear one. And we can estimate the period of the oscillation of the nonlinear one. There is another method that I like to use, not to make, to apply directly the theorem that I show you, the method that we call method of continuity. And sometimes it's very interesting to use this in the case where your parameter, sometimes the parameter can depend on the delay. In that case, it's very difficult to have a condition on the delay because imagine, I will come back to the main result, which is this. Yes. In general here, B, when you have a real problem coming from epidemiology or population dynamics, you have times exponential of minus R tau. Okay, that means this parameter depends on the delay. And when you put this, this cannot work in that case because if you increase the delay, this parameter decrease or increase. Then you cannot, because this result is true only if the parameters, especially this part, if the parameter A and B are independent on the delay. If they depend on R, you cannot put this. Okay, because you don't know if you if this can exist, because maybe when you move R, B and A can go to this part, and you will not have, or to this the other part, and you will not have the same result. This is why to mix this with the method of continuity, it's interesting. I will take the same equation and apply this method to show you that we can have results. I will look for local assembly. First, suppose that what that means, method of continuity, it's to take one parameter like delay and move it and check what happens and prove that we have continuity. That means if we look for eigenvalue or characteristic roots, they will have real part negative if we have stability, and they cannot jump from negative real part to the positive real part without crossing the imaginary axis. Okay, this is the principle. Then you look how they cross and find this threshold that give you to move from real part negative to real part positive. This is the main idea. We start by putting the delay equals to 0. The Mackay-Glass equation becomes this, okay, ordinary differential equation, and this has the same steady state than this one, okay. Then it's easy to see, because this I will do it by hand, because I will not make characteristics, because as I told you before, when you have ordinary differential equation, all the solutions of this ordinary differential equation are monotone, increasing or decreasing. There is no fluctuation, never. This is a general, in the sense, I will prove it again because it's nice result. When you have this x of t, where function g, all solutions are monotone. Continuous, the nonlinear function continues. If you have are monotone all the time. You need to know only for the initial condition. If for the initial condition the derivative is positive, the solution will stay positive. If the derivative for t equals to 0 is negative, the solution will stay negative. And this is very easy to prove. It's also by contradiction. If you have a solution by contradiction, if you have a solution and suppose that this solution is not monotone, what that means, not monotone, means that it will have this form, or this one is the same. There exists T1 and T2. Okay. I will put it here. Or this. That means there exists T1 and T2 such that I didn't put it well here, but it's when a solution is not monotone, you have this situation or this situation will happens for some time, T1 and T2. It's okay for all. If we don't have monotony, we will have this. It happens sometime. And this is never happen with this function. Why? Because here you will have x of T1, x of T2. They are equal. X T1 and x T2, they are equal. And as x satisfy this ordinary differential equation, then you will have yes, I forgot to tell you, to have this situation, it means that the derivative here times the derivative here is negative. They are opposite sign. That means x prime of T1 times x prime of T2 is negative. Okay, if this happen, what is x prime of T1? It's exactly g of x T1. What is x prime of T2 is exactly g of x T2. And this is negative. What is x T1? X T1 is equal to x T2. then this is j of x t1 square. And this is negative, it's not possible. Then this is contradiction. We will never have this situation for ordinary differential equation like this. Ordinary differential equation never create oscillations in one dimension. This is exactly the same, because here we have ordinary differential equation. That means we have to check only for one point, for x equals to 0, for example. Here, if beta 0 is greater than gamma, it will increase. If not, it will decrease. If beta 0 is greater than gamma, it will increase. If beta 0 is less than gamma, it will decrease. And this is exactly what I put here. This is will be positive if we have this, and it suffices for x equals to 0, beta 0 greater than gamma, then we will have the solution that increase and then go to the steady state, which is the positive one, because the steady state is given by this expression. For the first case, then we will have this. That means if and only if x of t is less than. If we are lower than the steady state, we will go to the steady state. If you are bigger, we'll go. That means this positive steady state is globally attractive in the ordinary case. This is what I put here. We deduce that if a solution satisfies for the initial condition x of 0 is bigger than the steady state, then the solution will decrease. And if the initial condition is less than the steady state, then the solution will increase. And then we have two possibilities. This one or this one, but this one will never happen because it will decrease to the steady state. As for ordinary differential equation, we don't allow solutions to cross each one. As the steady state is a particular solution, we will never have this crossing. Then, as they will not cross the steady state, x of t will go to the steady state. Okay, this is like a limit. If you have a steady state and the solution come like this, if it cannot cross it, it will tend to this limit, and we will have this situation. Yes, it's this situation is not possible to be equal to the steady state, because as here we have a solution, and the steady state is also a solution, and if x of t equals to x star, that means they will be equal for all the time, because we have uniqueness of the solutions for ordinary differential equation. Okay, this is a repetition because we know that then this is to do it by hand. Okay, but of course we can use characteristic equation, stability, and prove that the solution, if the delay equals to 0, go to this steady state. And the other case is exactly the same. Is to prove that the steady state is globally asymptotically stable if the delay is equals to 0. Both. Yeah, it depends. If beta 0 is less than gamma, 0 will be globally stable. If beta 0 is greater than gamma, this one will be globally stable. Yes. In infinite time, yes. Never, yes. Well, I am talking about this because when we will go to delay differential equation, we cannot do the same. We cannot, because for delay differential equation, solution can cross the steady state. Because as we have all the time oscillations, they can cross the steady state and turn to the steady state. For ordinary differential equation, cannot happen, never. Solutions cannot cross each other. But for the delay differential system, it can happen. This is the difference. I put this, it's only to show you after I cannot do it for delay difference. It's a mistake to do it. Okay, you have to change the method. The conclusion is this. If beta 0 is greater than gamma, this steady state is globally stable. If beta 0 is less than gamma, 0 is globally stable. Okay, now we add delay. What will happen? It's like do it by hand. Don't use this big result. Now we add delay. Can we transpose this, what I do here? For this, the answer is no, because I give you already example that we cannot make like a barrier to say the steady state will block the solution, then it will go, because the solution can cross the steady state and go to another place. We cannot do the same. We cannot use the same reasoning to study delay differential. This is one main difficulty in delay differential equation. Okay, in comparison with ordinary differential equation. The answer is generally no. We do not have with delay differential equation the same properties as with this. For example, the property of if the solution cross, then they are equal, doesn't work. For ordinary differential equation, it works. If you have one solution cross another, it's the same solutions. It can never happen. Okay, because it's unicity of the solution. I can add many things to explain this, but maybe someone can give me answer. Suppose that I have a delay differential equation, okay, with I have two solutions. And other one here. This solution go like this. I will put it in another color. And this one go this. Where the red solution will be the same after as yes, but infinite time, yes. If they cross it, there is no problem. We can cross and go. If they cross it again, but there is one case if the red one cross the black one, they will stay together forever. What is this condition? Sorry? When you have delay differential, they can cross. One solution can cross another one. But there is only one case. If they cross, they will stay together the same for all time after. What is this condition? It's only a geometrical condition. The condition is following. It's only if they cross for a time bigger than the delay or equal. If this, when they cross, it's exactly the time, in that case, they will never separate. They can cross like smaller and go like this and stay all the time, but if they are the same in an interval at least equal to the delay, they will stay forever the same. Exactly. Yes, this is exactly the explanation of this. Because for ordinary differential equation, the steady state is 1 point. If they cross, they have no choice. They will stay the same. But for delay, they can you can cross like a while, but smaller than the delay and make like this. Okay, this is possible. But if they cross during interval equals to delay, we can take this as initial condition and you have uniqueness of the solution. Now we add delay and we prove that we have conditions for stability of steady state without delay, and now we add delay. And we will concentrate only on this, the case where the positive steady state exists, beta 0 greater than gamma. And let's look for, in more details, the local asymptotic stability of this steady state. And you remember when we took tau equals to 0, in this case, the steady state is globally stable, but let's say locally asymptotically stable. And we make linearization. This is already did it. And we have this with B, the parameter B equal to this. And the steady state is this one. And the parameter here is minus gamma. The characteristic equation has this form. Okay? Here you can see that I put the delay because I want to see it like parameter that I can move. Okay, the characteristic equation is given by this. In fact, the solution lambda can be considered as a function of tau. And put this, I will show because this is very important result. What that means. I will give all the time the same example because it's very important result that help too much. It's like, suppose that delta and tau, they are real. It's only to understand. And suppose that you want to solve this all the time. Tau and lambda, and it's like tau lambda square minus 1 equal to 0. I took this to understand. Assume it's not this, but in general, we have this. As here, I say, in fact, I want the solution lambda can be considered as a function of tau. The same here. Can lambda be considered as a function of tau here? What is this? Equals to 0. This is, if I take this like tau, and this lambda, this is a circle. Okay? Can lambda be calculated in terms of tau? Here. Between this and this. It's a function. But it cannot be a function for all, because here, what that means function? That means you can calculate lambda in terms of tau. Each tau gives you one value, not uniqueness of the value of lambda for each tau. Here you have one, this one, and this one. But if we take, for example, the interval from -1 to 1 and only this part, here you can compute lambda, and it becomes lambda of tau equals the integral of minus tau square. Okay? And you see that when tau equals to 1, it becomes 0 and you stop. And now I don't want only to calculate lambda in terms, I want regularity. Has to be derivative, because I will need, I have to avoid these 2 points, because derivative here, infinite. Okay? Then the interval of existence is between -1 and 1. Okay? Now, I want to do it for a general equation, and I have this form. I want to calculate lambda in terms of tau. And there is a result. which tell you that you can do it. Here, how to avoid, what is this point and this one? It's only the derivative of this equals to 0 in terms of lambda. If you calculate derivative lambda, tau, lambda of this expression, what you will find 2 lambda, okay? And this give you, if this is 0, that means tau equals to 1 and minus 1. And this exactly this point. If this is equal to 0, this implies that tau equal plus minus 1. Then to avoid these 2 points, you have to avoid this and put something like this. And this is what we call implicit function theorem that I will show you here. We need this condition. It's around this point. Here you can never, this is more than that. I will maybe come back. What we know, we want to solve this problem and to calculate lambda in terms of tau. Okay, what we know that if tau equals to 0, I did it before, if tau equals to 0, I know that this equation has a unique solution, which is lambda 0 equals a plus b, and it's negative. Okay, I know that. And I know also if I calculate the derivative in terms of lambda, at this point I have 1. That means, because if the derivative is equal to 0, I am in this situation. Situation 1, you have this. The curve has this form. And around this point, you can never find a function. Okay, you have to avoid this point. And we have exactly what we want. The derivative of lambda in terms of lambda, it's different from 0. That means we will never be here. We are like somewhere place, and around this point, left and the right, we can find a function to have a unique representation, and lambda can be calculated in terms of tau. And this is, we call it implicit function theorem, because lambda is implicit and becomes explicit. Very interesting, because when you have this, we have this condition that I told you, then there is a neighborhood of this point and the neighborhood of lambda 0, such that lambda can be calculated in terms of tau. And this is a function now. And defined for neighborhood is this, and lambda neighborhood, and it becomes a solution. And why it's important, because when you function, that means each tau give you a unique lambda. Each tau give you a unique lambda around this point tau 0. And moreover, we have more than that, because we have that the function that I compute is also differentiable, continuous, and we know the derivative of the function. This is why it's very, very interesting. It's not only to know that you can calculate lambda as a function of tau, you can calculate also the derivative of lambda. Okay? It's very easy, this one, because you put this, you calculate the derivative here, partial derivative there, derivative of this, blah, 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 and you compute it, and you make inverse, and you calculate the derivative of lambda tau. And you know how your eigenvalue move, if they move from the point that you start, because you start at tau equal to 0, and you have real eigenvalue is negative. When you will move tau, you know if you will go to the left or to the right, how you go, until you reach the imaginary axis, you cross it, and this is very, very interesting result. Very easy to understand and to use, because you see, I can know if this derivative is positive or negative, and we call it implicit, because when you start, you know nothing, and when you calculate derivative, you have everything that you need to do it. Then we have this expression, and we know that this is bigger than this, and here depends on n. You can go on the right or on the left. To explain now, this is important. And this this result works almost all the time for this kind of. I put here the complex plan. Okay, this is AR, and this is R. For tau equals to 0, I am here. It's the parameter. It's this one, A plus B, and it's negative. There is only one eigenvalue. This is A plus B. It's negative. Yes. This is lambda 0. And what I know that from this, the derivative, it's depends on, let's say this is positive, but it depends on which situation. You will go like this or like this. Okay, it depends the condition of the parameter. Let's say we will go like this. Okay, what is more interesting, because here when you took lambda tau equals to 0, you have only real eigenvalue. But when you move tau, the eigenvalue complex appears. You have now two complex eigenvalue, one here and one here, and they move like this because it's positive. And as I told you that lambda is continuously differentiable, we will never jump. Maybe we will move, I don't know. But when because this, of course, it's only neighborhood of tau, not neighborhood of 0, around 0. But tau, we cannot see it here because it's like time. It's parameter time. The question now is when we will cross this imaginary axis. And this is the next step. We have, in fact, that the function is continuously differentiable. And okay, this is, yes, I choose this negative. Then if the steady state is make the stabilization, that means there exists tau such that we will be here. That means the steady state, sorry, there's a mistake. It means that the eigenvalue will cross the imaginary axis on some point that we have to determine. That means we will cross this imaginary axis. As we have a continuity, we cannot jump. Exactly. No, I put it here, yes. Negative, positive, yes. This is true, positive. That means there exists tau such that we will cross the imaginary axis. Now we have to look for this window. Which window we will cross? We have to look for omega that we cross this. How many omega we have? Maybe there is many. We can cross here, we can cross here, here, etc. We have to look. Then we look for this eigenvalue, imaginary root, blah, blah, blah. We put this, we take cosine and sine here also, and we have this system by separating real. Now we don't know if it exists or not. We are looking for the existence of this omega. But what we can remark that if, look here, in this, if omega is a solution, minus omega also a solution. Then that means there will always be a pair. If we cross here, we will cross also here in the same time. Then we will choose only one and make omega positive. Because if I omega is a root, minus I omega is also root. So we always have a pair of conjugate imaginary eigenvalue. We only look for one positive. And we can, we have all the time to avoid, because sometimes it can be, omega can be 0. And you cross here, and it's not good. When you cross 0, you have no oscillations. You cross 0 and you go, because 0 doesn't give you But in our system, we can see that omega can never be 0, because if lambda, it means lambda equals 0, you put it in your system, you will have gamma equals b. And this is a very singular case. We avoid this case, which is a critical case, and we will not consider this special case where gamma equals b. Then if you, I will start, come back here. If you put cosine square plus sine square, you will have 1. That means omega has to satisfy some assumption. Because of this, then that means omega square has to be b square minus gamma square. And now we can see that you can maybe answer, if gamma is bigger than beta, than b, what we have? If this term is bigger than this one, if this one is bigger than this one, that means this is negative. But omega square we have. That means omega doesn't exist if this term is negative. That means that if we can answer now that if gamma is bigger than beta, omega cannot exist, and we will never cross this imaginary axis. We will stay, and we will have stability all the time. You can increase the delay tau as you like, you will never cross the imaginary axis. That means you will have stability all the time. And this is what we call stability independent on the delay. And it was given by my theorem that I show you for the first and second step. There is no, okay, we will concentrate only on the case where B is bigger than gamma. That means we can have, there is only one window. It's given by this expression. If we have to go from here to here, there is only one choose. It's this one. There is no other choose. Okay, there is only one given by this. If B, this is, I call it omega, critical omega. But okay, now we know that, remember that we took this expression and we put this square plus this square equals to 1, and we cancel this tau. Now we have to find tau, because you find omega from this, but you have to find tau from this. Okay, because when you put this square this, you cancel tau and you don't know. Now you have to come back and put omega this value and find the time that you will cross this, because you know the window, but now you have to know which delay give you this crossing. And you come back to system and solve it again, because you put like implication. You have like sufficient condition. Now you have to find necessary condition. Now you have to find that. Now there is no choose. You have to solve one of this equation, and we choose this one. This one, then you make inversion, then omega c tau equals, and we find that as, this is a good question also. We have here many possibility of tau, because it depends on k. Let me go fast, because this case will never happen, only this. I put it here. I make like change b, blah, blah, blah. This is only because you have this condition, sine of omega c greater than 0, but you can use this expression to make condition on b. If this is positive, this is positive, that means, let me check how, yes, from this, sorry. This is positive. If this is positive, this is negative. If this is negative, as this is positive, this is positive. Okay, and you change this, because omega c, we know that it's positive. You change the condition on sine, on a condition on b. It's okay for you? Because the condition here is not comfortable to have a condition on sine. We want to have a condition on b. If this is positive, that means b is negative, because this one is always positive. Then we have this condition on b, and we have this. And we know also that b is greater than gamma. As b is greater than gamma, that means b is positive. We have only this condition. This you can forget. Sorry, I make mistake. Why yes, this we can forget, yes, because B is positive. We have only this. The problem now, we find many delays that make you crossing. Can you give me idea which one I have to choose? This is not mathematics, it's only logic. Which one I have to choose? I have many value of delay that make me crossing from crossing the imaginary axis. Which one I will choose? Sorry? Yes, the minimum, the first one. I will not wait. That means the first one, because as you increase tau, the first one give you, after maybe you will come back, but for the moment we are interested only to cross for the first time. Okay, then we take the smaller one, that means take k equals to 0. And you have, yes, this one. Make you crossing from the imaginary axis. And you have your threshold. Explicitly in terms of the parameter. Okay, voila. This is the one that after that, you will be here. Maybe we will come back, but this is another problem. The only thing that we know that we have threshold for the delay that make the eigenvalue go from the left to the right and cross the imaginary axis. Then we can make a theorem. If tau is less than this value, we have stability. And if tau is bigger than this, near, we have instability. Yes, this result is Hopf bifurcation. I do it by hand. But there is one problem I didn't talk about, because we say, oh, we cross, but maybe something can happen like this. You can go, but not cross really. You touch and you come back and you stay in this. It doesn't happen with this, but I will show you that we will calculate the derivative of lambda in this and show that it's positive. That means we really cross. Normally, we have to take this one and come back to our lambda, put it here, calculate the derivative, put it here, and show that it's positive. And we call this transversality condition for Hopf bifurcation theorem. You need this condition to show exactly that you cross. You don't come back near this point. And if you come back to the big theorem that I show you, you will not find the same expression, but we can find it making change of variable. At the end, you will find exactly the same. And all this, you can do it by hand. There is no, and for all differential system, we have this kind of things that you can do. Of course, you have to put, because the parameter B is a big parameter, but this is no problem. Yes. We find this, and we can prove that it's the same. This value is the same order by change of, because I didn't put B. Yes, I didn't put the value of B. I do it in general. If we put this value, you will find the same here. If you put, you take the explicit value of B and calculate all these stuffs, you will find the same threshold of the delay. I think we will stop here. Thank you. If you have questions or for break. You maybe sorry, slowly. I think it's not important to know exactly the value. It's the main idea how you start with tau equals 0. You have negative eigenvalue, and you know that your eigenvalue are function of tau, continues, and you increase tau until
Really, the beginning when you call all the data to zero, not be zero,
yes.
not see why, right? On the figure,
No.
why it was when it makes it circle,
Yes.
something that we cannot find.
Okay. Let let's take this. Okay, and you have lambda square plus r square minus 1 equal to 0. And you want to calculate lambda as a function of r in a neighborhood of r. That means left and... Can you do it here? Yes, this is r. This is lambda. Can you do it here? Yes, at this point. Can you do it? Of, for example, 1. If r equal to 1, can you calculate in this, near this, lambda as a function of r from this? No, you cannot. You can never calculate this because you see, you have no, even if you take very small, you can never calculate because you have something like this. You always have two values. For each r, you have a negative and positive one, and you are not able to do it. You have to avoid this point and this point, and to avoid them, is they are exactly given by this. If you have this derivative different 0, you can avoid them because, yes, yes, you can calculate. Because for yes, you have to avoid this point when the curve is vertical. The tangent is vertical. Always avoid. You can do all everywhere here. For example, here you can, here you can, here you can, here you can, but not here. Everywhere you can, here near you can. If you take a small, here you can make like a function. But when the derivative, because here, this point, when you calculate the derivative in terms of lambda, it gives you 0. This is why you cannot make the implicit function theorem. You cannot calculate lambda as a function of tau. And you need it because for all the expression that I did, you need this. And I put here a circle, but it's for everything, for all the functions. Yes. Because in general, when you solve something like that, if this is r and this is lambda, also if it's complex, something can be complicated. Huh? It's a curve, and you want to calculate lambda as a function of tau. You cannot do it here. Here you can, here you can, here you can, until here. Here you cannot, because this, what I will put red, it's a function. Okay? And here it's also a function. Until this point, etc. All the time when you have a vertical, the derivative of lambda equal to 0, you cannot do it. Okay, thank you. We have cake, yes.
Why you never told
I will come back to this system, but to do it, I will come back to the originary one, like that, because I already give this example. Yes, this one. You have 4 compartments. The first one is for susceptible population density of susceptible at time t with the age A. Age, as I said, it's not. It can be. It's age when we come back, when an individual come in this susceptible class. That means if you have immigration and new individuals come to susceptible, we count their age as 0 in the beginning. Okay, it's not real age. If there is no immigration, maybe it can be the real age. This is the variation of susceptible at time t with age A. This is the mortality rate. This is why you have here minus. It's proportional to the density of susceptible individuals. And H, it's what we can call it's the proportion of people that are get immunity by vaccine or protection or something like that. Then we move them from the susceptible class. And here there is the contact of susceptible with infected populations that get infected. And B is the force of infection, is the rate that a susceptible individual becomes infected in contact with infected population. And you have here, we take age from 0 to plus infinity. It's not, we can make limit of the age, but has no impact on the system. This is why we took age equal to 0. This is the population here, sorry, susceptible at age 0 come from, let's say, immigration, birth, etc., with the constant rate given by this lambda. I will talk about this after. And the second equation is for density of population that are protected at time t, age. It's not the same age here. It's age between 0 and tau. That is the duration of the protected class. That means, and when an individual come to this, are vaccinated or something like that, we count the age 0. And they spend a time equals to tau in this class. This is the mortality rate, natural mortality rate. I take here gamma p different from gamma s because mathematical point of view have no impact. For example, if we assume that people are protected has the same mortality, we can take gamma s equals gamma p. The flux between these two phases are given by this. And we assume that at the end of this phase, that means when an individual spend the time tau in this phase, he lost the protection and becomes susceptible. Here, when he reach, this is A, it's a time that, for example, PTA, T is the time, the real time, and A is the time that this individual spent in this phase, since when he come from 0 until A. That means when A equals to tau, this population are at the end of the protection. They lost this protection and becomes again susceptible. For the new protected people come from this class of susceptible with rate h. At each age, an individual come, okay, and we count their age 0 because the age is lost. When you come from here, you start again age 0. And why we take, I forget here, S, this is the total population of susceptible with age, because we, as here, it's uniform, it doesn't depend on the age. At the end is the same for each age. And you take all of them together, vaccine, because you vaccine each age. And this is why here we took capital S of T. Normally we have S of TA, another S of TA, another, but you sum all of them. This is why we took here all of them, the total population of susceptible at time T. It doesn't depend on the age. And you count again the age equals 0 in this phase. This is, it's not necessary to take here infected population with age because we are not interested in this model. Of course, we can, if there is no things happens in comparison with the other, no flux, you integrate this system and you will find this. This is why I didn't take it here. This is the infected population, comes from this part, because susceptible in contact with infected get infected, and you take all of them as for this. The force is beta, that this come here. This is the mortality, natural mortality, like this one and this one. And this is the people that was infected and they recovered, becomes, they are recovering and comes here. Now they are recovered. That means they are not they go away from the disease. Then you have this one, and also here you have the mortality rate given by gamma R. Of course, we can take gamma S, gamma P, gamma I, and gamma R equals and have the same mortality rate. And of course, you have some initial conditions.
The first question is A greater than 0 or greater than R?
This is greater than 0. Yes. Because the age becomes boundary condition. You take it.
And the last two,
Yes.
you make integration of the agent A, or you're assuming that it doesn't depend?
Both. It doesn't depend. Yes, you can make both assumptions, because you will see when we integrate this, we cannot integrate it. We need these conditions. For this, yes, you can integrate that. Everything becomes uniform and you get this kind of function.
And what when you put like the susceptible contact, all population P doesn't depend on it?
Yes,
Because the infection force there, like S small, and then for the infected one, it appears like S here.
yes, because each individual in contact with all the population infected becomes infected with this force. As beta doesn't depend on the age, on this age, by integration you have this, because you take all this population. Okay, you take all of them. Yes, it's not each individual, because as here we take all the infected population. You don't make a specific one. This is why here we have to take all the population susceptible that was in contact with infected people. This kind of system, as I told you, this is what we call hyperbolic partial differential equation, or transport age structured partial differential equation. But in this case, sometimes, for example, if you take the parameters depending on the age, you cannot reduce it to delay differential equation. Or sometimes if we take no linear function here, more complicated than this quadratic one, you cannot do what I will do here. Of course, this is special case. We can reduce this system to a delay differential system, but it's not always the case. Okay, there is a theory for this kind of partial differential equation. 20, you remember this? Do you want me to explain again? Yes? Yes. Yes. It's, of course, this in general, you don't do it like this. There is a theory to do it. Integration over the characteristic line, and you transform equation, blah, blah, blah. You solve and you find this. But I prefer to remember it, not to do it each time, to remember it like intuitively, real one. I will explain it again because it's after that it can be very easy to remember. This is a general for this kind of. If you have this minus gamma here, gamma p, gamma p, p of t a. Zero here, I think. A equals P0 A, and P of T 0 equals, I will not, yes, equal, I don't know, I will put B. Okay. This partial differential equation can be solved because first, it's a linear one. Okay, it's a linear partial differential equation. This is the initial condition, and this is the boundary condition. Okay, this is for time t equals to 0, it's given, and this is for h equal to 0, it's given by this. It's like the birth rate. Okay, and this we can solve it, and we have. I will put here gamma. It's only 2 because it's general. You solve it, and you have this. You can, the solution of this is given by P of TA equals this expression. Here, it's for the age, the time equals to 0, and here it's for the age equal to 0. To explain it, it's you make in the plan the time and the age. Here, the age is limited to tau. Okay, this is tau. And we take this is the first, it's 1. Okay, first, what we can see, you take any time and age as you like in R plus. You are sure to find it here somewhere, okay? Because it's like dense. If, let's say this point is here. This is for time and for age. The only thing, when you are here, time is greater than tau, okay? That means time is greater than the age, okay? And suppose that you have a population here that has this time and this age, E of t and age. And you want to see where this population come from. Okay, you know only one, two, three things. You know the mortality, you know, and it's the mortality, it's linear, it's like proportional. You know the initial condition, and you know the new population at age 0. And you want to follow this population. The method of characteristics tell you if you follow this line, which is parallel of this one, you will come back at the origin of the population. But here you come back here. What is this? In comparison with T and A. Exactly. That means if you come back, you will find the population at age 0. But this translation that you do from here to here, it's exactly T minus A. That this point is 0 for the age. Sorry, T minus A for time, and for age it's 0. Okay, here T is greater than A. This is why you have T greater than A. When you come back to age 0 and time T minus A. But this population comes from here, okay? But this population survive. This is why you have a coefficient exponential minus gamma A, because the duration of this phase is exactly A, okay? And this is why you have this, this is why you have this coefficient, okay? Now, if you take age and time here, this is time age. When you come here, you will be stopped here for T equals to 0. That means you will have 0. And what is the age? It's A minus T. Okay, because here the age is greater than time. What is the duration of this phase? Exactly T. And you have the same. Here you come back to time 0 and age A minus T. And they survive during T times. This is why you have this expression. And it's the comparison, the case take your age and time, it's exactly this. You come back and you say, I survived and I was born in this time. And this is what gives you the characteristic equation to solve this system. Then you have, this I never comment because it's make things easy, but it's not exactly for this system. We are interested by asymptotic behavior. It means for T large enough. This is why we take T greater than tau, not to have this and this condition in the same time. In that case, if T is greater than tau, as the age is between 0 and tau, this condition will be always satisfied. And then we will have only this expression. That means we wait enough time such that the initial population disappear. We wait enough time that population disappear, and when we come back, we will come back until not the initial population, but the population that was born at time T minus tau. And as we have the same age here that and survive during all this period. Then we have this, exactly. P of T tau, the solution is given explicitly by, as we know this, because this is the boundary condition. You remember here, P of T 0, the new protected people come from H proportion of susceptible at time T. As here we have T minus tau, we will have here T minus tau. Then this solution of the new protected people at time T, at the end of this protection, there is H proportion of this is survivor, and It's proportion of susceptible that was susceptible at time t minus time. And then, okay, for this, if you come back now to this system, and let's make integration of this system over the age. Okay, here you integrate over the age. Let's say that we can make permutation between the integral and the derivative because it's linear. Then you make this permutation because you integrate over this, and here becomes capital S. As the age disappear, this means the derivative of S. Okay, this one you integrate from 0 to plus infinity. We suppose that st plus infinity is 0. Population cannot survive. And the other one, then it will be s of t plus infinity minus s of t 0. Okay, this one, as doesn't depend on the age, it will be capital S of t. This doesn't depend on the age. Here will be capital S of t. And you obtain this. Sorry. Why I have this? Yes, but let me come back. There is something strange. No, it comes from this. Comes from this. Yes. Normally it's st0 plus st0, and we have gamma and p. And this one we know it comes from this. Then we have a delay differential equation. Of course, this happens also if you have a distributed delay. We have the same. Okay, everything it's okay. Then we do susceptible, but it's not finished because this, if we take this, now we will have the same function S. And we have this expression, which is delay and I. We can integrate also this one, but this one we can let it separately because we can compute it exactly in terms of S. We will not keep it like a differential equation. Okay, this we can let it for. This is why it doesn't appear in the system, because it's calculate exactly in terms of S, because it's given by this, and this we know it's this, and this we know it's this one. Then we obtain this system. It's okay. Also, this we can forget it because it's this one and this one doesn't depend on R. Then we can consider only the system SI. This is for the positivity. I already give you the method. You take in this component S equals to 0, and if the derivative is greater than or equal to 0, you have positivity. If S equals to 0, you have here 0, 0, and then you have gamma plus this. It's positive. Then this is no problem for S, and here you put this equal to 0. This equal to 0, you have positivity. And for this one also, if you put this equal to 0, you have positivity. I don't know why I put this. No, it's only because for the boundness, we use it. Maybe the last time I went very fast. Look, if you add this, and P, this one will be cancelled with this one. Okay. And this one will be cancelled with this one. And this one will be cancelled with this one. And what else? This one, I think it will be cancelled with this one. At the end, when you add the total population, you will have gamma plus gamma S, gamma P, gamma I, times I gamma, and we take, if you take the minimum, you have this estimation. Okay, gamma minus lambda minus gamma n of t, and this is when you have this inequality, it's very easy to solve. Because normally we have this. It's to put the same variable. Ah, yes, you have this. Okay, because we want to have something greater to measure, not to take minimum. You have this. Yes, when you have the minus, the maximum becomes minimum, and the minimum becomes maximum. If you want the maximum, you have to take the minimum. Okay, because there is minus. Because we need this inequality in this sense to make the boundness. Sorry? Yes. And with this is okay for, this is very, you put this other side, you multiply by this expression, and you see that this is the derivative of the expression that you put here. And then you have this is the same. This is the same, and you integrate from 0 to t. By integration, you have n of t exponential minus n0, I put it here, and you multiply by exponential minus gamma t here, and you find this expression. Okay? Here, why you have this? Because you integrate this one, give you this minus 1 over. And here, yes, you put, you multiply inside. You have n0, and if you multiply inside, here it becomes, and you can see that this one is positive. Okay, and if you can see that if this one is greater than this one, it will be n0 here, because if this one is greater than this one, you put here n0, and this will be cancelled with this because there is minus. Okay? If this one is bigger than this one, then you can measure this by n0 here, and put n0 with n0, as there is minus n0 exponential, it will be cancelled with other, and you will have only n0. If this one is bigger than this one, you do the same, gamma n, and you cancel, and you have this. That means it's always the maximum between this one and n0 in the initial condition, and it is bounded. This is why what we, in fact, I think we have here, but I didn't talk about uniform boundness. What that means, uniform, it's independent on n0. But uniform unbounded is only for t large enough. If you take time large enough, you will have all the time, even if you take n0 very big, yes, you will have something independent on n0. And then, as the total population is bounded, each population in each class is also bounded, because they are part of n of t. Okay, now I will go to the other part, because this is my system. Here we put something about steady state, but I will go directly to other one. Yes, this one. And I want to study the local asymptotic stability of steady state. And I will, because this system has two steady states. There is one steady state without disease, what we call disease-free steady state. That means I will forget this R. I will let it without. If we take here I constant equals to 0, it satisfies this one. And if you put here I equal to 0, you will, and take S constant, you will find this one. Okay? This is a free, this is steady state. Okay? And the last time I told you that there is a number in epidemiology that we call R0 show you that if R0 is less than 1, the free disease steady state will be stable, and if R0 is greater than 1, it will be unstable. Okay, that means the disease will grow. We will prove this result. R0 is given by this expression. I will prove that this is the threshold that gives you stability of this steady state. To do that, we make linearization. Remember that, linearization around the disease-free steady state. The linearization is given by this. You calculate the derivative at each. For example, this I have to show you. From here, let's calculate the linearization, how to make linearization. This one will be 0, because you take the derivative, we are here on S. This one is 0, okay? Now this one, we make derivative in terms of S, then we have a constant, minus gamma S plus H. As we make a derivative of S, we have to put S again, okay? This is when you have it's exactly the same. Linearization of this is the same. This is what I want. You calculate the derivative, and you put again the function. Okay. This is why the linearization of this part is exactly the same. This is different. You have to make derivative in terms of S first, and second derivative in terms of I. When you calculate derivative in terms of S, what you get? Minus beta A. But you have to take it on the steady state. I is equal to 0. Then this disappears. And now you calculate the derivative in terms of I, and you put it in the steady state S. Then you will have beta S bar E of t, because you I of t. This is why you get this. Sorry? No, it's not a bar. This is, you calculate the derivative and you add this. It's always like that. Maybe I will show you for ordinary. Look. If you have this, okay, when you make derivative, sometimes I use the same notation. This is why it can be confusion. Let's keep the same notation, but for linear. You put like this, you calculate the derivative on the steady state, and you put x of t. Okay, you calculate the derivative on the steady state, and you put. Here, you have to calculate the derivative of this, you get this, and you, etc. And here, you calculate the derivative of this on S, then you get A bar, and you put S. You calculate the derivative in terms of S, you get beta A, and you put S. As the derivative A is 0, disappear. You calculate the derivative on I, it is S, you put on the steady state, and you put I again. It's always like that. You put X again, and you get this. As this is linear, it's the same. You calculate the derivative of this, you get this constant, and you put S of t minus tau. I think the confusion here, because I use the same notation. Normally, I have to use other notation this is linear, but in general, we use the same notation not to change. Here, the same. As this linear, you calculate the derivative on I, and you put I, and here the same. As it's quadratic, you calculate the derivative on S. As I bar equal to 0, it disappears, and you calculate the derivative in terms of I, and it's beta S bar, and you put I. And you get this, this linear system. And the characteristic equation, you look for, I didn't develop here, but I will put it here because it's important. How to, you have choose between two things. Or you come back to the formula that I give you, trace of the matrix A, determinant, blah, 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 and you find it. Or you do it by hand. I think it's better to do it by hand because it's not difficult. How to do it by hand? You put S of t, you look for a solution like this, and for I of t, a solution like this. And you put on your system and you solve. As we have S prime, then we have lambda, exponential lambda t, S0 equals minus gamma S plus H exponential lambda t, S0 minus beta exponential lambda t A0, and plus H exponential minus gamma S tau exponential lambda t minus tau S0. And you do the same for the other one, lambda exponential lambda t E0, I0 minus mu plus gamma I exponential lambda t A0 plus beta S bar exponential lambda t I0. And here, first I will cancel this because it's the same. And here I cancel it and I let only minus gamma tau. Okay? And I do the same here. I cancel because it's, and I will put all of them on one part. Then I will have lambda here plus gamma S plus H, and this one also minus exponential minus gamma S tau, all of the exponential minus lambda tau, sorry? Gamma P, yes. Why I put gamma S? Gamma P. Okay, all of this times S0. And I have this one also, plus beta S bar I0 equals to 0. I do the same here. I will start with, there is no S. Okay. I will put it here. Lambda plus mu plus gamma A minus beta S bar, all of them. Okay, and this, I will put it like a matrix. Multiply by S0, I0. Then you have lambda plus gamma S plus H. I will put it like this, minus exponential minus gamma P tau. No, I cannot. H minus H exponential minus gamma P tau exponential minus lambda tau. This one, the other one is here. I will take, this one is 0, and this one I have lambda plus mu plus gamma I minus beta S bar. I will take it off to see. And here I have beta S bar. This matrix times S0, I0 is equal to 0. And we look for non-trivial solution. That means no 0, 0. If this is invertible, you have only 0, 0 as solution. Then this has to be non-invertible. Then the determinant of this has to be equal to 0 to have a non-trivial solution. Because if this, the determinant of this is no 0, it's invertible, you put it in the all side, multiply by 0, you have S0, I0 equal to 0. We don't want this because we know it. To have a non-trivial solution, determinant of this has to be 0. And determinant of this, it's this times this. And you have exactly this. You have exactly the expression that I put here. And this is the characteristic equation that give you non-trivial solution. Non-trivial solutions. And what we can remark, look, this expression, it's there is only one solution. It's lambda equals minus this plus this. And this is exactly this expression. That means if R0 is bigger than 1, lambda is positive. And we have unstable steady state. This is exactly, then there exists a positive real characteristic root, and the steady state is unstable. If R0 is less than 1, this one is negative, but we have to study the other one. It's not finished yet for this. Then if R0 is less than 1, this is negative, then there exists a negative real characteristic root, but we cannot conclude on the stability of the steady state because we need to study the other part. Oh. No, let's study this. Because we have a general expression of this. We already have, I will come back, maybe I will put it here and come back to see if it's stable. Or maybe do it by hands. Let's do it by hands, okay? Sorry? Or someone to come to do it by hands. What you suggest to use as method? Remember, lambda is a complex number, and we look for to be, if it's negative, real part is negative lambda. Yes. What? No, it's because they are complex. You cannot make. Anyone has a suggestion? Which method we use? Because we have now we know. We want to study the stability in general. This is all people that are working in delay difference equation. This is the first thing that they do. They say, let's take tau equal to 0 to see. If tau is equals to 0, what happens? Maybe I will be in. Sorry? Lambda is complex. This is good. That means we are, and let's look for the window that we cross, okay? Imaginary axis. This is good because if tau equals to 0, we will have lambda equal minus gamma s. This is very good, and it's negative. That means in our complex plan, we are here. We are negative. Then if we start to increase tau, we will not jump. Why? Because we can. Yes, and the implicit function theorem. Let see for tau equals to 0 if we don't have this vertical, if we can have a function, if lambda can be computed in terms of tau or not. And remember what we calculate to do that. I will. We have delta R. All right, there is a. Okay, can push. Tau lambda equals to 0. Okay, and we know that delta 0 of minus gamma s is already solution. Then around this, if we can, because the curve is like this, if we can not have this vertical, we can calculate lambda in terms of tau. And to satisfy this, we have to calculate the derivative of lambda on this point, okay, to see if we don't have this, but we have something. Let's calculate this on 0 minus gamma s. Okay, someone tell me what it will give, the derivative in terms of lambda of the characteristic 1, yes. For tau equals to 0, okay. No, calculate after we put tau equals to 0. Then? No, because we calculate in terms of lambda. This is minus tau multiplied by this. And it's 0, because tau it's 0. We calculate on 0. This. Then it's 1. That means it's different from 0. That means implicit function theorem tell you that tau, lambda tau is continuously differentiable. Then you can follow now tau and find this is the implicit one. If you are able to do this, because you have delta tau lambda equals to 0, it's like a curve, and on this point you have something here, not infinite, because lambda is vertical and tau is horizontal. It's like we put it like a turn to see it. It's like tau here and lambda here, not to be 0. Then you can calculate lambda in terms of tau. As we can calculate now, we are to look for if we will cross imaginary axes or not. Then let's look for if this exists. Let's put it in our system, what we will find. We will find, I will only, of course, only this part. You can help me. I omega gamma s h minus gamma p tau, and this is exponential minus e omega tau. Okay, equals to 0. This is, I will let it like this, plus and this is cosine and sine, okay? Let's take real part and imaginary part. Then we have the real part is this one. But it's the new one. h1 minus exponential minus gamma p tau okay, this is plus h1 minus exponential minus gamma tau cosine omega tau equals to 0. This is okay. And the imaginary part, omega minus, because there is here minus h1 minus it's okay? Let's calculate cosine and sine because it's more easy. Then cosine omega tau, it's this is cannot be equal to 0 because tau now is greater than 0. Okay, then we can divide by it's minus gamma s over h 1 minus exponential gamma p tau. No problem. It's and the sine, it's omega over the same. Let's make this square plus this square to calculate omega because we are looking for omega. Then we have gamma s square over tau square plus equal to 1. Okay, I put this in the other side and I calculate omega. I will do it here. Then we will have omega square h1 minus exponential minus gamma p tau square equals 1 minus and multiply by this. Then I have omega square h minus gamma. Okay, this is a square. I can make factorization. Then h1 minus exponential tau minus gamma s multiply by h1 minus exponential minus gamma p tau plus, it's okay, this square minus this square. It's okay. It's I put this factorization. Square, square, square. It's okay. Yes, there is here only one problem. It's yes, this. Let's check now. Because I forget. It's finished. Because look, this guy can exist only if this is positive. Okay? And this is negative. This is always positive because this is positive, this less than 1, but this is negative. Because I forget to put the condition, this plus this has to be greater than this for the existence of susceptible. That means we will never, as this positive, omega square will never exist. That means we get stability all the time. It's independent on, for this steady state, tau, the delay can never make this steady state unstable. As he is stable for equal to 0, as we will never cross the imaginary axis, he will be stable for all tau. And then it finishes for. That means there is no condition on the parameter to make him unstable. He will be stable all the time. And that means each time that this guy exists, he is stable all the time. After that, next, I will show you that he is globally stable, not only locally, because this is, we can construct a Lyapunov function for this steady state and prove that he is always globally stable. Also, this is the disease-free steady state. After that, we will study also the endemic steady state, the steady state with the disease, and prove also that when this new steady state appear, he is also locally stable and also globally stable. That means any initial conditions go to this steady state. I don't know if what time is it. What I want to do next time is to talk about global stability and Lyapunov function, how to construct Lyapunov function, and monotone dynamical system. It's a very important part, how delay differential equation can generate monotone dynamical system. And to study the stability of equilibrium, it's if we have a monotone dynamical system, it's more easy. Let me come back to. In fact, this is a monotone dynamical system. This is why he's independent on the delay, because as I told you before, there is only one part where there is a delay. It's this part, and this part it's increasing in terms of S of t minus tau. When you have a positive delay, in the linear case, it's always, if there is steady state, he's always globally stable. This is the case here. But sometimes you forget to do it, but here it can be immediately. Exactly this. And for monotone system, we can say also it's independent on the delay. If you check stability, of course, global stability. If he's locally stable for tau equals to 0, he will stay because when you have monotone dynamical system, you have always this. You cannot find omega. That means you will never cross the imaginary axis, and you will stay all the time. No, it's more complicated because what I want to say, generate monotone dynamical system. It's not because sometimes if this is positive, we know that it generates, but I have to define precisely what that means because for system it's more complicated. Okay, what is monotone is exactly this function. This the function that for when you have a solution like this, you take each piece of solution between t minus r and t, and you translate this piece here, and this is what is monotone for each time. You see, this is more, I will give you a condition to have this. This is the piece. Imagine that your solution go like this for time. And each time you cut this and you put it here, tack, tack, tack. And you forget this and make simulation. You will see like this snake moving like this. Okay? Even if this it's monotone, doesn't mean that this snake monotone, because this part can be maybe, even if this it's not really monotone, maybe this part can be like this. Okay? I never, sometimes maybe it can be better to make simulation of this. I don't know how to do it. When you move tau, each time you take this piece and you translate it on the interval minus R0. Each time, tack, tack, tack. And you forget this and you move time to see when you start with initial condition, how this snake move. To see exactly what that means, monotony. And to have this behavior of solution, there is some conditions on the delay given by Hal Smith and many people. I don't know if it's easy to simulate this. You take any functions and make movie about this to see. No, to see this snake how, because it's, yes, in figure like this, between minus R0, and you translate, because it's continuous, and you see how it moves. Yes, can be very nice to explain what that means, monotone dynamical system. Okay, I already talked about this, but now to give a definition, what is local hop bifurcation? Maybe you already, this is a famous notion. We always talk about bifurcation, hop bifurcation. What is exactly hop bifurcation? First, you have a nonlinear delay differential system in general, and you have a parameter, alpha, inside of this system. This parameter can be the delay or other parameter. It is a real parameter, and you have a nonlinear function that is differentiable and the derivative is continuous. And you assume that you have a steady state, which is for all value of this parameter. This steady state can depend on this parameter, but the only thing, if you move alpha, this guy will be all the time steady state. Okay, we make this equal to 0. You make first I explain what is hop bifurcation. You move this parameter, and you are in the stable. This is what I did. You are in the beginning in a stable part. That means your steady state is unstable. You move alpha until your steady state becomes unstable. And hop bifurcation tell you that if you do this under some conditions, when it will be unstable, periodic solutions will appear exactly at this point and will stay a while, even if you continue to move your alpha. And this is very good result. It's not only becomes unstable with existence of periodic solutions and for non-linear system. And the theorem gives you also the period of this periodic solution. But what are the conditions? First, steady state, and second, use linearization. If we calculate linearization for each parameter in terms of this steady state, exactly what I did before. We linearize and we have a linear system. We have a characteristic equation as I did before. Let's say this one, and the theorem is the following. If for value of parameter, it's like tau equals to 0, for example. No, sorry, it was not tau equals to 0. It was the limit. Assume that there is one parameter, it can be 0 or other. After that, you can make change. It's not necessary to be 0, okay? If at this parameter, you have the existence of imaginary root. In general, there are two. There is something disappear. Oh, no, sorry, see here. You have this one and this one all the time, okay? Imagine that one parameter give you one imaginary root. They are simple. Simple, that means if you calculate the derivative of the characteristic equation, this eigenvalue is not yet, eigenvalue again, is not solution again. Solution only for one order, okay? That means you have delta of 0 I omega equals to 0, and the derivative is different from 0. Cannot be the solution, the root of this, and same time the root of the derivative. That's what means simple, okay? All the other roots are not multiplied by this. It's only to avoid this multiple root. This has happened all the time. It's not a problem. And suppose also that this that we already talked about, if you make lambda as a function of this parameter alpha, suppose that this branch of roots, when you take tau alpha equals to 0, you have this steady state, exactly this one. And the derivative of the real part of lambda at this point is different from 0. Can someone explain you what that means, this? Where we are here, when alpha equals to 0, where we are when alpha, the parameter, equals to 0. In the complex plan, where we are exactly in the imaginary axis. Huh? Exact. If this, what that means, this derivative is different from 0. We are, I will, exactly. But why I took different from 0, not positive? Because you go from the left to the right, it should be positive. Why I put only this? You have explanation? Yeah, derivative of the real part, because imaginary part is like this, the real part is like this. No, if yes, because you know in this axis, this is the real and this is the imaginary. If this is different 0, even if you have this, it's okay, you pass. If this is equal, you will have this and you will do like this. Okay, only the real part. But why it's different from 0? And we know that it will be like this. Because if it's different from 0, it will be positive. There is no other way. It's not necessary to prove that it's positive, because if it's different 0, it is positive. Not lost your time to, because we are from negative to positive. We are from left to right. This is, sometimes you can find in some book positive or different 0. It's not, because we know that if it's different from 0, it's positive, cannot be negative. If you have this, then for alpha near 0, near when you have this steady state, this equation has non-trivial periodic solution with period goes 2p over imaginary part of the root that you find. Oh, no, there is a mistake here. Omega, yes. This is omega. Imaginary part of this, it's exactly omega. The period is 2p over omega. Okay, this is a very good result in Hopf verification that was, I think, in 1930 was by, and this is very, very interesting because it's, because you can do it only locally. Okay, yes, yes. And there is global Hopf verification. You can show that you have periodic solution everywhere. Here, you have to be near, close this parameter, blah, blah, etc. Yes. This is we can do it for this example and prove that, because you can see this example, if I told you, can you find periodic solution? It's impossible. How to find periodic solution for this system? And there is a good way. It's only to take the linear part and try to satisfy the theorem of Hopf verification, and you will find a periodic solution. How to do? It's exactly what here I took tau equals to 1 because the parameter is not necessary tau, can be tau. Here the parameter, there is only one, a. We will look for, we take this and we will, what we have to look for? It's to find parameter a such that the characteristic equation has imaginary roots. and satisfy what we call transversality property. This, okay, let's do it for this. We look for, here I look for all this, but after that we'll concentrate only on omega. Let's look for eigen. What I forgot to tell you. This is this equation is linearization around 0. Okay, we take linearization. We will show that there is periodic solution around 0, not around, because we can do it also for 1 or -1. But I will show you after that one, around 1 and -1, there is no periodic solution. There is only stability or instability. We can never have this. But around 0, we have periodic solution. Okay? Then we look for blah, blah, blah. We have this system. And here we have real and imaginary parts. We can see it's always like that. If omega is solution, minus omega is also solution. Then we will concentrate only on omega positive. It's okay for all of you? Here, I am not looking only for omega because I want to do two things in the same time. To see the sign of mu and to find, after that, to take mu equals to 0 and find omega. This is only to go fast. Because why I do this? Because I want to cross the imaginary axis, but I want to cross it from the left to the right. That means I want to find the parameter such that I cross from the left. That means I has to be before the real part has to be negative and becomes 0. This is why I used both mu and omega. We look for, first, let's take mu equals to 0 and look for omega. And suppose that, I don't know if there exists, but suppose that I will look for a parameter that give me the existence of omega. Okay? Then I put mu equal to 0, and I put in my system mu equals to 0 and a equals to a0, and I have this. Okay? I suppose that this parameter is different from 0, because if it's 0, I will have omega equals to 0. I don't want omega equals to 0. Okay? Because it's I have to have imaginary roots. Then as a0 is different from 0, then we can solve this, and we have omega 0 is p over 2 plus kp. Okay? That means I have many solutions, because k is... but if I use this second, as I have a0 from here is omega over sine, if I put here, I will have this. Okay? Because sine of p over 2 plus k, p is -1 power k. Okay? I have this. And since a0 is positive, I can take only the positive part. That means, but the same problem as I told you, which one I will take? I have many solutions of a0. The first one, yes. We will not wait. Then we take the first one, this one. And if a0 equal p over 2, what is the eigenvalue? Come back here. If a0 is equal p over 2, I have this equal to 0, and then as k equals 0, I have p over 2. Then the imaginary root that I will cross is this one, a p over 2. It's given here, because I take k equals to 0 to have this one. It's okay? Then my imaginary root that when I will cross, I have both now. I have the parameter that give me this crossing, and I have the eigenvalue. But what I don't have, this is the good question. I know that I will cross at a for the parameter equals p over 2. I know where I will cross, when I will cross, but there is something missing. What is? I know that for my parameter, I will cross here. And I know the value of my parameter. But there is something missing. I don't know if I will come from the left to the right or from the right to the left, because I check for one parameter. I didn't check if my parameter A is less than P over 2 if I am really in the negative real part. Okay, I have to check this. And this is the next step, because I look here, I don't say anything about where I was before, for A before. But I will prove this. When I am before P over 2, this is why I use this. I will prove that my mu is negative. It's completely negative. I do it here. Come back. I will prove that when A is less than P over 2, between 0 and P over 2, the eigenvalue, my real part is negative. I take the characteristic equation and I do it by contradiction all the time. Assume that my mu is positive. Then this is less than 1. If mu is positive, the exponential of minus mu is less than 1. If I put it, what? No, omega is P over 2. Sorry, this is, no. This is before. Omega is, we don't know. Because we are before the parameter A, because when A will be here, mu will be equal to 0. And omega positive. Yes, this is right. Omega is positive. We can assume that omega is positive since the beginning. Omega cannot be equal to 0. Why? Because omega equals to 0 only if A equal P over 2. This? Okay, I don't know. Yes, it comes from, because here, sorry. Here, when you develop this, it's, yes, but omega, it's cosine and sine. Okay? It's a real part. Yes, I was fast here because, sorry, I have to come back to, yes, in fact, I use this. If mu is positive, this, yes, I use this. We can maybe do it here. If mu is positive, this less than 1. Okay? Remember this expression. I will use it here. As this is less than 1, then this is less than A. I come back to show you. It comes from this, because omega equal to this. And this one is less than 1. Okay? And this one is less than P over 2. I don't know. This one, yes. It's okay? As omega equals, this is less than 1, this is less than 1, and this is less than P over 2. That means omega is less than P over 2. As also omega is positive, as omega is less than P over 2, cosine will be positive. Then we have a contradiction, because this positive, and yes, we obtain mu negative. And this is contradiction because we assume that mu is positive. That means mu is negative. This is very strange by contradiction. You want something, you assume that it's not exactly what you want, and you find the opposite of what you... Sorry? Yes. And after that, you say, no, this is what I get. It's the real things, not... this is very tricky things, because you assume that mu is positive and you get mu is negative, and you say mu is negative. But I don't know if it can be equal to 0 or not. And since we cannot get, because this is very easy to see, mu cannot be 0, because if mu 0, omega will be less than P over 2. But omega, it's the first one is P over 2, when mu equal to 0. Then the conclusion is when A is here, mu is negative. That means we are really in the negative real part, and we cross. The only thing that now we have to show is if it's really the derivative or the real part is different from 0. That means if we cross from the left to the right and not come back, we have to prove that the eigenvalue cross. Yes, we can go back. We don't know how. We know that we cross. To do that, this is now I put A0. I am on this point, on the imaginary axis. This is I already proved it many times, so we can prove it also here that we can calculate the eigenvalue in terms of the parameter A. Okay, we have the real part and imaginary part, and now we have we know that lambda at this point, point what we have application, give you imaginary root. The characteristic equation, and I will calculate. This is I have two kind of or apply the formula that I give you in the implicit function theorem. I will come back because I never do it. I give it because it's general, this one. You can apply directly this, but it's not necessary. You can calculate it, get it again. This is what I will use directly here. Because I don't know this expression. I know that it exists, but I am not. To do it, you calculate the derivative of this, and you calculate this one dividing by. Then if we calculate the derivative of this is this one, and derivative of this is minus a exponential minus lambda a multiplied by derivative of this. Okay, with exponential, and we put the exponential on the other part. I will maybe do it again because it's not clear. We have lambda prime plus, you make derivative in terms of a. It's exponential minus lambda a plus minus a lambda prime a exponential minus lambda a equals to 0. And you take this with this, then you have 1 plus minus a exponential minus lambda a, and the other one you put it in the other side. Okay, and you have this expression, and you multiply. This is only by minus 1, and let's check that lambda is simple. This is important. I told you before, lambda has to be simple. That means this guy, if you take a equals a0, the derivative of this has not to be 0. This is what it's important, because when you have there is in the proof of the theorem of simplification, as you have to divide by the derivative has not to be equal to 0. This is why the problem is and if it's equal to 0, you have problem to come back again. To prove this by contradiction again, suppose by contradiction that this derivative equal to 0, that means this equal to 0, and it's not possible because it has exponential of minus lambda 0 equal to 0, and this is equals to minus 1. It's not 0. Then we have one part of Hopf verification satisfied, and yes, we have this. Then it is simple. Now we have to prove this. This is exactly what I prove. You put here, this come from this. Okay, you divide by this expression. And you have this expression. How to get this? It's only because you have the characteristic equation. Okay, the characteristic equation is, I don't remember, it's lambda minus a exponential lambda a. I don't remember, you put this and you divide. No, there is no a. Yes, there is a. Something like that. And you calculate this and you have this divide by a. Yes. And you put it here, or you multiply by exponential here, and you calculate this expression. Okay, it gives you this. And for a0, this is eigenvalue ip over 2. This is p over 2, and this is ip over 2 plus 1. you multiply by conjugate, blah, 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 this conjugate of this, and you get this. This is only a calculation. It's not complicated. It's complex. And you get this. And its transversality property is satisfied. Then we have Hopf bifurcation. And the equation that I show you before has periodic solutions when A is close to pi over 2 parameter, and the period is close to 4. And this is always the case. Why the period is close to 4? Almost always the case. It's 4 times the delay. Yes. This is what Hopf bifurcation told you. The period is close to p over imaginary part of lambda. That means the period is close to, it's almost equal to 2 pi over omega, okay? And in our case, p over 2, then, and why it's almost always like this, because when you have this, I take like this, okay? And you make linearization, blah, 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 etc. When you put linearization, you have, I will put like this. Always this. Okay, when A is the derivative, I don't know which steady state, let's say. Okay, and this is the same. This is why always the same equation. And the parameter A will be again P over 2. The parameter of bifurcation when you get this, because it's exactly the same. When you come back, for this equation, yes, this is always the same equation. And this is why bifurcation is always around here for this equation. If let's say that I will take 0 as a steady state. Okay, let's take something like that. And the parameter will be the derivative of f on 0. And you will find that the bifurcation that you get here, because the equation is independent on the system, you have this, you do the same, and you will find A0 equals P over 2, and you will have eigenvalue P over 2, and you will do the same, and exactly 4. And this is a very, very strange situation, because for all the Lie differential system, it's always the periodic solution are always the same. You go in the same periodic solution, because all the time you have this, of course, this kind of ordinary differential system, because they have the same linearization. And as the non-linear system, we get periodic solutions from this. This is why we have, and of course, I took here A. If I put here not 1, but R, I will have exactly the same, but at the end, the period will be 4 times the delay. Four times the delay. If the system is destabilized, he get periodic solution with period 4 times the delay of the system. And this result we can find also sometimes for the system. There is like kind of uniformity for the periodic solution that we get. I think I will, what time? Oh, yes. I will stop here if you have questions or comments. It's very interesting because we find periodic oscillations that now you can come back to this, say, oh, if I take A near P over 2, I will have periodic solutions with period 4, oscillating around 0. Of course, it's not finished because there are many other theorems to go on the right of this parameter A0 to see if the period, what happens for the period, if it's increasing, decreasing, or if we keep stability, if there is a limit cycle, if and this is another problem because we need to develop the no-linear part using what we call normal forms. You develop and until like series here, it's more easy because it's polynomial, and each parameter of your development give you information about the size of the period, amplitude, and stability also of the limit cycle that you get. Okay, thank you.